everyone. In the previous class, we have studied about the expression for torque, that is dipole in a uniform external field, and also about the continuous charge distribution, the linear charge density, surface charge density, and the volume charge density, and also expression for electric field due to a continuous charge distribution. So in today's class, we are going to study about the Gauss law, and whoever is watching the video, please subscribe, like and share it with your friends. Okay, coming to the Gauss law. Gauss law states that the electric flux phi through any closed surface is 1 by epsilon naught times the charge enclosed by the surface yes. The electric flux phi through any closed surface is 1 by epsilon naught times the charge enclosed by the surface yes. This is the statement of Gauss law. Electric flux phi through any closed surface is 1 by epsilon naught times the total charge enclosed, that is Q by epsilon naught, the total charge enclosed by the surface yes. This is the statement of Gauss law, and this is the mathematical form of Gauss law. Let us study about the applications of Gauss law. The first application of Gauss law is expression for electric field due to infinitely long straight wire. Let us consider a long straight wire for this. This is the long straight wire, and let us imagine a cylindrical Gaussian surface area. Around this infinitely long straight wire, the charges are uniformly distributed on this long straight wire. L is the length of the wire and R is the radial distance at point P. Okay. Then the flux through this Gaussian surface area, it is taken as phi is equal to electric field into area. So electric field is given as E, and the area of this cylindrical surface is taken as 2 pi r L. That is phi is equal to 2 pi r L. Take this as equation number 1. The total charge enclosed in this Gaussian surface, it is taken as Q is equal to lambda into L, where lambda is the linear charge density. Lambda is the linear charge density. We already studied about the Gauss law, that is phi is equal to Q by epsilon naught. In place of Q, substitute the value of Q as lambda L. You will get lambda L divided by epsilon naught. Take this as equation number 2. Okay, from equation number 1 and 2, from equation 1 and 2, we can compare equation number 1 and 2, and we can take it as E into 2 pi r L is equal to lambda L divided by epsilon naught. Here L and L gets cancelled. From this equation, we can write E into 2 pi r L is equal to lambda by epsilon naught, or E is equal to lambda divided by epsilon naught into 1 divided by 2 pi r into 1 divided by 2 pi r. This is the expression for electric field due to infinitely long straight wire. Okay, vectorially we can represent this one as, vectorial notation for this expression is, vectorially it can be represented as E bar is equal to lambda divided by epsilon naught into 1 by 2 pi r into n cap, where n cap is nothing but radial unit vector. N cap is radial unit vector. Okay, this is the first application of Gauss law, expression for electric field due to infinitely long straight wire. For that, let us consider a infinitely long straight wire. Just imagine a cylindrical Gaussian surface around this long straight wire. Then the electric flux through the surface is taken as phi is equal to electric field into area, where this area is 2 pi r l. The charge enclosed by this surface is lambda into L, because where lambda is nothing but the linear charge density. We already studied the Gauss law, that is phi is equal to q by epsilon naught. In place of q, substitute lambda L and consider it as equation number 2. From equation 1 and equation 2, we have E into 2 pi r l is equal to lambda L by epsilon naught, where L and L gets cancelled. Remaining is E into 2 pi r is equal to lambda by epsilon naught. Or we can write it as E is equal to lambda by epsilon naught into 1 by 2 pi r. Vectorially, it can be represented as E bar is equal to lambda by epsilon naught 2 pi r into n cap. N cap is nothing but the radial unit vector, and this is the first application of Gauss law. The second application of Gauss law is expression for electric field due to uniformly charged infinite plane sheet. So for this, let us consider sigma. Let it sigma be the surface charge density. Okay, let sigma be the surface charge density. So to find out the electric field due to infinite plane sheet, let us consider a rectangular parallelepiped. This is the rectangular parallelepiped. It is having the two surfaces, surface 1 and surface 2. These two surfaces are having unit vectors, where the surface area 1, it is having the unit vector normal in the minus x direction, while the second surface is having the unit vector normal in the plus x direction. Okay, so these two surfaces, the electric flux adds up each other, that is E bar dot delta S bar. In previous class you already studied about the electric flux. Phi is equal to E bar dot delta S bar. So this adds up and it becomes E into delta S, because theta becomes 0 here. Okay, and the charge density is given as Q is equal to sigma into A. A is nothing but the cross sectional area of this rectangular parallelepiped. Sigma is the surface charge density. Q is equal to sigma into A. Already we know that the phi, since it adds upon for the two surface areas, phi is equal to 2 EA. Take this as equation number 1. We are having Q is equal to sigma A. Coming to the Gauss law, phi is equal to Q by epsilon naught. This we already know. Here in place of Q, substitute the value of Q as sigma A divided by epsilon naught. Take this as equation number 2. So from equation 1 and 2, from equation 1 and equation number 2. When you compare equations 1 and 2, we can write it as 2EA is equal to sigma A divided by epsilon naught. Here A and A gets cancelled, remaining is 2E is equal to sigma by epsilon naught, or we can write it as E is equal to sigma by 2 epsilon naught. This is the expression required here. Again we have to write the vectorial notation for this expression. It is nothing but vectorially we can write it as vectorially E bar is equal to sigma by 2 epsilon naught into n cap. Okay, where this n cap is nothing but the unit vector normal to the plane. N cap is the unit vector normal to the plane. Okay, this is the second application of Gauss law for the infinite plane sheet. Is it clear? The third application of the Gauss law is expression for electric field due to uniformly charged spherical surface. In that, the first case is the field outside the shell. For that, let us consider point P. It is outside the field of the shell. It is at a distance r from the center O. Since the point P, at all the points the spherical symmetry is relatively equivalent, for a given surface at every point the value of E bar, that is the magnitude of E bar and delta S bar, these will be parallel, and hence the flux is taken as phi is equal to A E bar dot delta S bar. It is taken as E dot delta S because theta is equal to 0, and hence the total Gaussian surface S is equal to 4 pi r square. The total Gaussian surface S is equal to 4 pi r square, and the electric flux phi is equal to E into 4 pi r square. Already we know the Gauss law. According to Gauss law, phi is equal to Q by epsilon naught. Okay, phi is equal to Q by epsilon naught. Comparing these two equations, or let us take it as equation number 1 and equation 2. From equations 1 and 2, from 1 and 2, E into 4 pi r square is equal to Q divided by epsilon naught, or E is equal to 1 by 4 pi epsilon naught into Q divided by r square. So this is the expression for electric field outside the shell, when the point lies outside the shell, field outside the shell. And also vectorially we have to denote this, or we have to write this expression. It is nothing but vectorially E bar is equal to 1 by 4 pi epsilon naught into Q by r square into r cap. Okay, where r cap is nothing but the unit vector, where r cap is the unit vector. This is the expression for electric field due to uniformly charged spherical surface. The second case of the third application is field inside the shell. Let us consider sigma as the surface charge density. surface charge density. Let sigma be the surface charge density and P be the point inside the shell with the radial distance r. Okay, since the charges are present only inside the shell, only outside the shell, and no charges are enclosed by the Gaussian surface, therefore we can say Q is equal to 0. Since the charges are present only on the surface, these are present only on the surface and no charges are enclosed in the Gaussian surface, therefore the charge enclosed by the Gaussian surface is 0. That is, according to Gauss law, phi is equal to Q by epsilon naught, but this is equal to 0, and the value of E into 4 pi r square, this will also be equal to 0, which implies that E will be equal to 0. Okay, E equal to 0 only when the value of r is less than r. Therefore, we can say that the electric field due to uniformly charged thin shell is 0. Thin shell is 0. Thin shell is 0. And this is the second case of the third application of Gauss law. And this completes the first chapter. And to study the previous topics of the first chapter, go through the previous videos of my channel. So whoever is watching the video, please subscribe my channel, like the videos and share with your friends. Thank you.